Today, we're going to be talking about signal processing. And so what that encompasses is, in general, having generative sounds and applying effects to them. And I've got some code here. I'll just run through it real quick. This synthdef is almost the same as the one we saw last week. The main difference is that the envelope is now a percussive envelope, so it's a finite duration envelope, and it sounds like this. And I also have this pattern, just recalling some p-bind stuff from the end of last week's lecture, using that synthdef, random MIDI note numbers, random durations, random amplitude levels, and random release times. It's one of the bleepiest things you can imagine. All right, so we'll come back to this shortly, but just to start things off here, let's say we defined a synthdef. I'm going to try to do this really fast. We will just make this 800 hertz. And there's lots of unit generators throughout SuperCollider. There are various delay unit generators which will delay some input signal, which can be used in various combinations to create echoes and ping pong delays and flangers and comb filters. Actually, these don't have any sort of feedback, but then there's also these comb delays, which it's basically the same thing, but with feedback, so you can specify a feedback coefficient or technically a decay time. There's also a variety of built-in reverberators. We have Freeverb, which is I think a mono input, stereo output. No, I think it's mono in, mono out. And then there's Freeverb 2, which is stereo in, stereo out. There's also Gverb. So lots of interesting options here. And on a very basic level, if we want to apply an effect to a sound, let's actually go ahead and do this. Nope, we have to do this. So this is going to sound like this. All right, let's make this envelope even shorter. All right, oh, let's make it stereo. Right, basic sound. I think sort of the simplest but also the worst way to apply effects is to build it right into the same synthdef. This is problematic for a number of reasons, but let me just show you the construction of UGens and how to interconnect them. So let's say we want to, let's do Freeverb 2. So Freeverb accepts two input signals, the left and the right channel. You're required to sort of split them up into two mono channels. Mix, room, damping. Let's go through these one by one, I guess. So we'll just say sig equals different ways to do this. We'll just do it like this. Freeverb2.ar, and now sig is it's two identical channels in left and a right, but they're the same thing. But nevertheless, we're going to break them up anyway, like this. So we're providing Freeverb with the left and right channels separately. Mix, should all probably be familiar with mix, but 1 is 100% reverb and 0% dry, and 0 is no reverb at all. So we'll just stick to something like this, and we'll make it a nice big room. I don't know what the maximum. I think the maximum is 1. It's just like some ginormous room, and that's probably fine. And this is going to sound like this. Okay, so the problem is, right off the bat, we have this envelope, which is a short percussive envelope, which has done action 2. So as soon as the envelope is done, the sound goes poof, and that's no good, because we want to be able to savor this lovely long reverb tail. So we can make the done action 0, and now we'll hear the whole thing. But this synth never dies. And if we make more, eventually we're just going to overwhelm the server, because even though these synths decay down to something which is indistinguishable from silence, computation is still happening. All of these free verb2s are still active and running and calculating sample values, and eventually we're going to run into some serious problem here. So if we force ourselves to do this, building the effects straight into the synth-def, then we have to do something really ugly, like putting a separate type of envelope somewhere here. We'll just have this line go from 0 to 0 over 8 seconds, and it has a done action too. It's not involved in the synthesis in any way. It's just here to terminate the sound when a sufficient amount of time has passed. So I'm just pressing Command period to get rid of all the synths. And now we get a nice long reverb tail. And after 8 seconds, the done action 2 kicks in, and this synth goes poof. But I'm only showing you this example so you can get a sense of how to construct signal processing. And we've seen this already with filters like LPF, HPF, where we just have an input signal. Those are signal processing UGens. You have an input signal, it gets plugged in, and you provide additional parameters, and it modifies the input signal and outputs that signal. So, in conclusion, this is a problematic approach. It's one, CPU considerations are an issue, because if you make a pattern that generates lots of these synths, for every single synth, you have an instance of reverb. And reverb is generally not a cheap effect, especially if you accumulate a whole rich, dense texture. So CPU problems. And also this awkward problem of having to build in an extra envelope whose sole job is to end the sound. And this time here is going to vary based on the room size and things like that. So it's just a big mess. The correct way to do this, and I don't think it's an exaggeration to call it the correct way, is to use buses. So a bus, generally speaking, is a term and a concept which is common to not just SuperCollider, but all sorts of digital audio platforms, DAWs, analog mixers. And to put it very simply, a bus is a place or a location to which signal can be written and from which signal can be read. And it's a device that allows different processes to share an audio signal. For example, passing a signal from some generative process to a bus, where some signal processing device reads from that bus. And this is really a flexible paradigm, because you can have one generative unit writing to a bus and then many processes reading from that bus. They can all share it. Or you can have one generative process writing to many different buses. Each one of those is being read by some different signal process. So it's this lovely, elegant network of signal passing from one thing to another. So in SuperCollider, there are audio buses and control buses that are pre-built into the server. As soon as you boot the server, they're all available. And we can get the number of audio buses with s.options.num audio bus channels, and the default is 1024. Imagine a mixer with 1024 channels. That's basically what the SuperCollider server is. 1024 audio channels. The control channels, there's even more of those. These are for control signals, and because control signals output one sample per control block, there's a lot more overhead. So and I have never found the need to change these numbers. This is very adequate for almost every application. If we open up the meters, what we're looking at here is 2 of these audio channels for output and another 2 for input. And the default, well, let me back up a step. The way SuperCollider conceptualizes these audio buses is that there's a block of them starting at index 0, and some number of them starting, so 0 and 1, or maybe 0 through 7, which are designated as hardware output buses, which means they are associated with physical hardware output channels of the audio device you happen to be using. That might be your built-in sound card, and for Mac OS, it's built-in output, or you might have an audio interface connected with a different number of outputs and inputs, but there's a certain number of audio channels which are associated with the output channels of your device. And then, following that block, there's an additional block of channels associated with the physical inputs of your device. And the default, as of right now, and I think as this has been the case for many recent versions of SuperCollider, is 2 output channels, 2 input channels. So that means audio buses 0 and 1 correspond to the left and right outputs, your speakers, basically. And 2 and 3 correspond to microphone inputs on your interface or built into your computer or whatever. And the remaining channels, 4 through 1023, are so-called private audio buses. And I think you can get the number of those as well. How does this go? Num private audio bus channels. And this is the number of audio bus channels minus the number of output bus channels minus the number of input bus channels. Right? So we have 2 of these, and a total of this many. So the remaining, those are all private. And the private audio buses are just there for you to use as you see fit, to secretly pass signals from one synth to another behind the scenes. And these values here, this and this, are the values that SuperCollider uses to draw the meters when you launch them. It says, okay, how many actual physical hardware outputs and inputs do I have? So we could theoretically change these. Let's say if we say, we'll set this equal to 8, and this equal to 8. And then in order for these option changes to take effect, we have to reboot the server. And now if we draw the meters, we've got 8 outputs and 8 inputs. Not actually, though, because I'm still just using my HDMI output here, which I believe is only capable of transmitting 2 channels out, and I'm using my Focusrite interface, which has 2 channels in. So even though we tell SuperCollider, hey, we have 8 channels in and 8 channels out, it will go along with it, but if I play something to any of these additional output channels, we won't actually hear it. But if you have an 8-channel audio interface and you're doing octaphonic sound, then you would connect that interface and plug all of the jacks in the back of that interface into speakers or whatever. And you would also need to tell SuperCollider, I actually have 8 channels of output that I'm working with here. And so you would make this change, and then you'd be able to send audio to all 8 of those output channels. This means you have slightly fewer private bus channels, but again, 1024, that is plenty to work with. And just because I'm going to return these back to their original values, just so we're working with default conditions here. And let me draw a picture, just to reinforce this a little bit. So here is the server, this mysterious looking box. And we can imagine it as having 1024 audio buses, and also 16,384 control buses, but we're not going to draw those. And they just look like these. I'm just going to draw them as I've done a similar drawing in the past. I think it was week 6 on last year's introduction course. I'll just draw a few of them, and I just imagine them as little pathways. Oops. Just that you can, write signal to and read signal from. And so here's 0, 1, 2, 3, 4, 5, 6, et cetera, and then here we have 1023 for a total of 1024. So these 2 channels here are our outputs. So here we have little speakers, right, left and right, to represent where these channels go. And I could plug 2 microphones into my interface. Here's one microphone. Here's another microphone. And those go in here and here. And so that means all of these, right, 4, 5, 6, etc., are private audio buses. So we can write signal to them. We won't hear it, but we could use some other process to read from those channels. So let's actually get a little bit closer towards doing that. What I'm going to do is play some signal. Let's just do pink noise. And let's make a synth-diff. Actually, you know what? How do I want to do this? We'll start with pink noise for now. And we're going to say bus 19. Normally we put an argument here called out. That's the best practice. But just for demonstration, we're going to say 19 sig. Okay, so we are playing 2 channels of pink noise, right? 2 channels to bus 19. And so now we're going to open up the scope. And what we're looking at are, we're starting at audio bus index 0 and looking at 2 channels. So this is bus 0, this is bus 1. If we expand this to 4 channels, you can see here's my voice on the very next channel. Right? That's me coming in on audio bus 2. And we can confirm this over here. Right? This is technically, this says 0, 1, 0, 1. But in SuperCollider's brain, the inputs are 2 and 3. And we can confirm that just by looking at the meters here. So let's look at 4 channels starting at bus 18. And look at that. On 19 and 20, we've got pink noise doing its thing. Right? We can just amplify that a little bit so we can see it. Right? There it is. And if I press Command period, we kill that synth and it goes away. So again, just because we play some signal doesn't mean we're going to hear it, depending on what bus we send it to. And also notice that even though we sent this to bus 19, it was playing on 19 and 20. This is the default behavior when you send a multi-channel signal to a single bus index. SuperCollider says, okay, I've got this many channels, so I'm just going to start at this bus and then just put the remaining channels in ascending order. And we can do the same thing with control signals, just to demonstrate here. We can use out.kr, right? Out is just another UGen. It can run at the audio rate or control rate. And we'll say, put it on bus 47, like this. And we're going to play this. And now if we go to our scope, we're going to look at control channels. We'll go up to bus 46, and there it is. Okay? So these buses exist for us to do whatever we want, and they're just locations that we can just pipe signal over here, pipe signal over here. Let's now do an example where we're actually going to read from a bus. So what I will do is I'm going to modify this example here. And we're just going to make a function. Forget about this. Forget about that. Okay. We want to read signal from a bus now. And to do that, we use the counterpart to out, which is, of course, in, right? In. We want to read an audio signal from a bus. And right now there's nothing, we could, the only signal that's actually awake and doing stuff is this one, my voice, right? And we could read the signal on audio bus 2 and play it out of the speakers, and you'd hear me coming out of the speakers, and there might be even some feedback. Who knows? It might be very exciting. Maybe we'll do that, and maybe we won't. But for now, in.ar takes 2 things, a bus index and a number of channels. So for example, if I put 19 and 2, what this synth will do is generate a signal by reading audio from audio buses 19 and 20. It will then pass them through this reverb and write them to buses 0 and 1. Remember, this is a 2-channel signal. We're breaking it up into left and right, and freeverb outputs a 2-channel signal. And this is a 2-channel signal, so it goes to 0 and 1. And we're just going to play that. And you don't hear anything because there's no signal being written to bus 19. It's empty. But here, temp 11, that is the synth that was created by playing this function. And so now all we have to do is, I will just grab this and bring it down here. And just for fun, I should have picked a lower number, but now we have to look at all these. We can't selectively look at channels here, but 19 and 20 are down here somewhere. We will tuck this over here, and we just need to say go to 19, because we already have an argument defined in this synth called out, which tells the synth the synth where to go, where the output destination is. So now we have reverb. And I'm seeing multiple channels here. I think this might be, no, we're summing here. Yeah, but I'm not actually sure why. How many channels are there? I think there must be something wrong with my synth because I know I have this dupe 4 here, but I'm summing here. Mystery. Let's do that. And okay. We're just going to do this. This is a very messy fix, but oh, you know what it is? Well, at least here, the mic is picking up. No. Yeah, okay, so I fixed it. This is fixed. It's just we see a little bit down here because the mic is picking up a little bit from the speakers, but I don't want to spend time here trying to figure out why my synth is broken, but I'm just saying, you know what, just forget about it, just output the first 2 channels. I'll fix this before I upload it. Anyway, so I hit command period so we can create this again, and then signal flow, at least on a superficial level, should be clear here. We have a process writing to bus 19 and another process reading from bus 19 and applying reverb and sending to bus 0. Good, okay. The next thing I want to point out is that using numbers like this is messy. It's not a good idea because when you have a moderate-sized project or a large project where you have lots of different effects, it is very annoying to have to say, okay, 19 is reverb, 74 is this, and it's just picking arbitrary numbers. It's just hard to keep track of what's what, and you're very likely to send something to the wrong place, and then it just becomes a nightmare to debug. Better is to use the bus class. So we can create a reference to an audio bus on the server in the language. And we use the bus class for this. And interestingly, this bus object, despite being intimately tied to the server, is not a server-side object. The server doesn't even need to be booted for us to create these objects. The buses already exist on the server. Here we're just making a reference to them so that we can use them and give them meaningful names in the language. And they need to know the server on which the buses exist, so that's usually going to be lowercase s, and then the number of channels. And this is where you, as the user, need to be very conscious about the channel size of your various signals. Like if you design some sound and it's stereo, and then you design some effect that's going to process that signal, that it should have a stereo input, and you should be using a stereo bus. Because if you mix and match and get some mono stereo things mixed up, SuperCollider is not going to present you with any warnings or like, hey, I noticed this is a 2-channel signal, but it's a 1-channel bus. SuperCollider assumes you know what you're doing. And when if for example, you allocate a mono bus, and then you write a 4-channel signal to it, you will write all 4 of those channels to the remaining adjacent buses, and who knows what that's going to do if you're not expecting it. So the point here is be conscious of the channel size of your inputs, your outputs, and your buses. They all need to match. If they don't, probably nothing's going to blow up, but you'll get unexpected results that'll be hard to explain if you're not totally sure what's going on. So we make one of these, and it tells us in the post window, this is an audio bus. Its index is 4, its size is 2, and it's on the localhost server. And we can even query it and say things like reverbBus.index, num channels, I think. So we can ask it all sorts of things. And the way the bus allocation process works is it knows how many channels are reserved for hardware outputs and how many channels are reserved for hardware inputs and how many buses have been previously allocated, and it takes the next available block. So for example, if we wanted to make a delay bus, right, we can just say, give me another stereo bus. And it says, okay, I'm already using 4 and 5 for this reverb whatever, right? So I'm going to take 6 and 7. And then we can keep going, et cetera, et cetera. One thing to watch out for here is that if you are rehearsing or debugging and you run this code again and again and again, SuperCollider thinks that you're asking for another bus, and it doesn't care that you're overwriting the same variable name with something new. It says, well, okay, well, I already reserved these, so next pair, next pair, next pair, and eventually you will run out of buses. Like if I want a 200 channel bus, yeah, okay, it just says, okay, I have no more. You have all of my buses, and so this can happen eventually if you're rehearsing and rerunning code many, many times. And so the question is, how do we get SuperCollider to forget about all of these buses? And the way we do that is by saying s.new bus allocators. And this just says all the buses are now designated as being available. So when we run this code again, we're back where we started. So wherever in your code you are allocating buses, it's always good to begin that block with a refresh, with new bus allocators. That way you can run this code as many times as you want, and it's just saying, okay, I'm going to reallocate these buses 4, 5, 6, 7, and you can do it again, 4, 5, 6, 7. So you'll never run out as long as you prepend with this command here. Okay, so we've got a reverb bus called reverb bus, and so now we could let's actually make this into a synth-def. Now, the wrong thing to do is this. I do not recommend doing this. And the right thing to do is to declare an argument, which we can do like this. And I think this is OK. But I think an even better strategy is to just put some value in here and specify buses when the synth is created. Don't try to do it in the synth-def. The synth-def is supposed to be this agnostic, generalized recipe for synthesis. It's not the actualization of a sound or a processing effect. So, if you're doing the argument style, I would do something like this. Right? And this, I'm almost positive, will not work. You should not be using environment variables in argument declaration default values. So something like this is good. Something like this. KR is fine too, right? It's all fine. Something like this is totally fine. So we have a signal which is reading. It's going to be reading from 2 input channels from somewhere, right? Whatever we provide. It's going to apply this reverb. Maybe we want to provide some arguments here as well to change the color of the reverb. And we should do something like this as well. I know this looks a little crazy because it's like, whoa, we're reading and writing the same bus, but these are just placeholder values. This is the approach that I've come to like over the years. So there we go. We now have a reverb synth-def. And this is what I mean. We're going to say in reverb bus, out 0. There we go. And we have some junk synth-def. Let me get rid of that. Let's just make this again. Okay, I don't know what that was. It was left over from something. So now we've got a reverb synth reading from reverb bus. And so now we can go here to our synth and say, we just need to say out reverb bus. And I need to do this style here. And that should work. And let's look at all the channels. So there's the dry signal getting written to buses 4 and 5, which are our first pair of available private buses. And there's a synth reading from those buses, applying reverb, and writing to 0 and 1. And those channels are associated with our hardware outputs, which is why we actually hear something coming out of the speakers. And if we go back to our pattern, we can say, you go out to the reverb bus, and just supplying yet another pattern value, a key value pair to be supplied here. So I didn't need to evaluate that. I just got knee-jerk reaction. So this pattern turns into an event stream player, which creates synths, each of which sends its output signal to the reverb bus. And we've got a synth listening and playing to bus 0 and 1. Yes?
If you have multiple buses writing to the same bus, like the output,
yeah.
Will they add together?
If you use out.ar, the default behavior, if you have like a sine wave and pink noise both writing to bus 0, the behavior of out.ar is to sum the output signal with whatever else happens to be on that bus at that time. Okay, I want to transition now to a concept called order of execution. This is really important because if you're not aware of it, you will try to apply an effect and everything looks right. You have the right bus, in, out, but you hear nothing. And let me cook up a quick example, make another synth def here. What I want to do is just make some singular synth that is continuously generating sound. I'm gonna modify this synth def a little bit. So let's put that in here. And we'll call this pulse sus. So it's just going to be okay, try to make this simple. Let's do this and this. And we don't need that. We don't need to pan. We don't need that. And need that. Okay. So that synth def sounds like this. Okay. Command period. I forgot to give it a name. Hopefully, okay, I think this will be something that we'll be able to hear reverb when it's applied. So we actually still have our reverb bus. It's still an object that exists. And let's go down here to copy and paste these. I'm making a real mess of my code. Everything's kind of out of order. This is the curse of an interpreted programming language where it encourages you to just go all over the map and delete and change and stuff. So I will clean this up. But basically, let's go ahead and make this synth, the reverb synth, and then we'll say make the reverb bus and do that. Oh, okay, wrong synth. And here's another beautiful part of separating out your generative and effects, is that we can just completely destroy the source, but the reverb effect remains alive, and it's still just doing its thing, right? It receives some signal, and it's spitting out this reverb. So we can, I should have put an envelope maybe on this so we can fade it out kind of nice, but you get the idea, right? Yeah. Okay. Right. Very, very classic computer music, I know. Okay, so what happens if we just carelessly do things, command period, just refresh everything, and we'll make this. Okay, so there it is, right? It's playing its signal, bus 4 and 5, and then we'll make the reverb. What? Unbelievable. What? Why is this not working, right? It's outrageous. We have our source sound. It's playing to the reverb bus. We have our effect reading from the reverb bus. We can see the signal right here. Why is there nothing here? This is a crystallized example of order of execution. So order of execution refers to the order in which synthesis nodes on the server are processed, control block by control block by control block. So here is, we have a lot of these, don't we? Yeah, so many. This window is a graphical representation of what's called the node tree. It's a list of all of the synthesis processes that are active on the server. And at the top, we have the head of the node tree. And at the bottom, we have the tail. So for example, at the very head of the tree, we have this localhost input levels, which is something related to my meters, wherever they are. Yeah, over here. And I could just close these and those go away. And we can close our scope too for the moment. So these are the processes right now. We have a group. I'll talk about groups in just a second. And then at the head, we have the reverb. And then below, we have the generative synth. And SuperCollider processes audio in blocks of samples. This is how all digital audio platforms work. They process like 64 samples at a time. So 64 samples, and then the next 64 samples. Sometimes it's 128. It's just some power of 2. And in SuperCollider, the default is 64. Right? And okay, let's go over to our diagram here. And let's say we just play a sine wave to bus 0 and 1 and pink noise to bus 0 and 1. So we have some stereo sine wave, and it goes here and here. And then maybe below that, towards the tail of the node tree, we have pink noise. And that goes to bus 0 and 1. Now what this means on every control cycle, every 64 samples worth of time, which is a very, very, very small slice of time, SuperCollider processes samples from head to tail. So the sine wave gets calculated first and written to bus 0 and 1. Then the pink noise gets calculated and written to bus 0 and 1, where it is summed with the sine wave. And on that cycle, we hear a lovely mix of a sine wave and pink noise. And if we were to switch these, it wouldn't matter, because A plus B equals B plus A. So when there's no passing of signal from generator to processor, the order of synth nodes on the server really doesn't matter at all. They'll all just get processed and spit out, right? But if we have two processes that depend on each other, like our pulse sus and our reverb, well, pulse sus is getting written to 4 and 5. And reverb is reading from 4 and 5 and writing to 0 and 1. Right? So this is where it's very important. We have to make sure that pulse sus is closer to the head of the node tree than the reverb. So this is the correct order. Right? Sources towards the top, effects towards the bottom. Because what happens is on one control cycle, the server first runs into pulse sus and says, okay, I'm going to calculate these samples and drop them onto these buses, 4 and 5. Then it encounters the reverb, where it reads buses 4 and 5, which actually have signal on them, and then processes them and puts them on 0 and 1. And then out comes 64 samples worth of reverberated pulse noise. Great, perfect, that's exactly what we want. At the end of every control cycle, all the buses get wiped. So every 64 samples, SuperCollider says, zoop, everything's 0, and it starts again with the next 64 samples of all of the synthesis nodes. So if these are in the wrong order, then the reverb says, okay, I'm going to read from 4 and 5, right, and write to 0 and 1. But of course, at the beginning of a control cycle, there's nothing there. So the reverb just is pulling silence and reverberating silence and outputting reverberated silence, which of course is silent. And then the pulse says, okay, here I go, I'm making my sound, and it writes signal to 4 and 5. But of course, it's too late, because at this point in the control cycle, nothing is going to read that signal. And then the buses get wiped, and the process starts again. So that is why we don't hear anything with this particular configuration, even though everything else looks to be, exactly where it's supposed to go. Right? It's still going. The problem is that the nodes are in the wrong order. Okay, so we're going to command period this. And so the reason you'd think this might work, right? So we make a synth, and there it goes. It's on the node tree. And then we make the reverb. The default behavior is to put new synths at the head of the node tree. And so this is a segue into targets and addActions. Targets and addActions. When we make a synth, we say synth.new or something. There are actually 4 arguments that synth.new expects. The first is the synth.def name. The second is an array of arguments. And we're familiar with both of those things. But there's a third argument called target and a fourth argument called addAction. And the combination of these 2 arguments determine where on the node tree that synth will get placed. Now, the default target is the server, which translates into the default group of the default server, which is this gray box here. And the default addAction is the symbol add to head, which, as the name suggests, adds to the head of whatever the target is. Right? So let's unpack this a little bit. So let's go ahead and make the reverb synth first. Right? And we could put this in other places. We could say, okay, the target is the server, and there are 5 addActions we could do. There's add to head, which is the default, add to tail. This is going to look exactly the same because there's nothing in this group. So the tail and the head end up being the same position. We could also do add before, and see it ends up before, right? That the target, which is the default group on the default server. And there's also add after, which goes right after. And there's also, I'm not going to do this one because I think it's going to mess something up. There's add replace, and this will replace the target with this new synth. And the target is the server. I think it's going to destroy this default group, and I don't want to destroy the default group. But those are the 5 addActions. Add to head, add to tail, add before, add after, and add replace. But the target doesn't have to be a server. The target could be a group, a synth, an integer, in which case it gets interpreted as the node ID of that, as the synth or group with that node ID. For example, if we just make the synth, so it has this number 1227. That's an automatically generated number. That is the node ID of this reverb synth. So we could go here, and one valid thing to do here is to say U1227, add before. Right? So that's good because it goes and finds node ID with 1227 and adds it right before, so that'll work. This is, of course, a very clumsy, who knows what the node ID is? We're going to look at the node tree every time we want to add an effect. I'm not doing that. So we can just say, what we should do, command period, we'll say reverb synth equals this synth. Now it has a name, right? So now, over here, we can just say your target is the reverb synth. And I want you to add before. So this is much better because we can provide our own name and reference the target that way. Let's do command period here, and copy this stuff for a second. Bring it down here, and I'm going to make two groups. Source group new. Whoa, what? No, of course, that's completely wrong. I had a moment. Ignore that. This is what I meant to type. That was complete nonsense what I just typed. Don't look at that. Pretend that never happened. So we're just making a new group. And there it is. We've made a group. And just to back up a second here, groups are nodes, just like synths. They're entities that live on the server that exist within this order of nodes. And groups don't make any sound, but they are very useful devices for organizing other synths and groups. They're basically containers. Like we have this default group, which is kind of always there. And we made this group, and the default behavior is to add it to the head of the default group. And so that's why we have this here. And we can say effects group equals group dot new target addAction. These are the two arguments that a group expects. So we'll say source group add after. Right? And we'll watch the node tree over here. When we do this, there we go. We made a group, and it got put right after that one. And so now this is convenient because we have a group and another group that are always going to be in this order. So we can just dump all of our generative synths into the headmost group and our reverb into the tailmost group. And then order of execution is going to be automatically handled for us because these groups will always remain in an appropriate order. So we don't have to worry about managing the synths. So now we can say your target is the source group. And it doesn't even matter where it goes in the source group because it's always going to be above the other group. So there it is. It's in this group. And then we can take the reverb synth and say your target is the effects group. And that works just fine. And even if we didn't have a name for this synth, we can talk to the group and say source group dot free all. And what this will do is free all of the nodes inside of it, but the group itself will remain. So we'll see this synth disappear, but the group remains. And this is just in case we had lots of synths, like if we just did this a bunch of times. Let's free them all. Okay? And I'm going to give, to wrap up here, I'm going to give you a little teaser, a figure from my book, just to give you a little visualization. It's a very big TIFF file here. Though it usually doesn't take this long to open. Oh my god, the suspense is killing me. Okay, let's just open it in like preview or something. Hopefully that'll be better. My computer seems to be slowing down. This might be related to the fact that I'm also screen recording right now, and it's just a lot of pixels. Ah, okay, good. If we just look in the middle of this vortex of node trees, this is our starting position. We have a default group, inside that a group of our own, and inside that a synth. And then these 6 branches show the addition of a new synth based on various combinations of targets and addActions. So you can go back to the video and watch this. But basically, if we look in the upper left, if we make a new synth and specify its target to be group 1000, and the addAction is add to head, you can see it goes to the head of that group, so the topmost thing in that group. The same thing would happen if the target were the synth and the action were add before. And you sort of get the idea. If you just look, you don't have to digest it all right now, but you can come back to this in the video and just kind of take a few minutes to study it and understand. So this is a really important set of concepts here. Buses, input-output UGens, groups as a way of organizing things on the server, and probably most importantly is order of execution. The sources have to be closer to the head of the node tree than the effects that process those signals. And I think that's gonna do it for this lecture. I'm going to assign one more homework assignment, and it's going to be, you're basically going to take these concepts, but I'm going to give you a generative synth-def, one effect, and another effect. And you basically have to use buses and groups to route them in various types of configurations. So taking these concepts just a little bit of one more step further. Yes?
Does anybody see the name of a group in the node tree?
Well, groups don't have names. You can't give a group a name because, with synth, there's synth-def, and there's a name associated with that. But groups are just these kind of entities. They have node IDs, and those are visible on the node tree. But you cannot actually name a group, which is unfortunate. Right? It's just the server does not have access to your language side variable naming scheme. It's a good question, though. And I will also write and publish the final project prompt sometime today or tomorrow. And I might do like I'd feel remiss if I didn't give you like a MIDI and GUI assignment, but maybe I'll make those optional or extra credit or something like that, right? I do think you should reinforce the topics that we'll cover between now and the end of the semester, but I know it's been a lot so far this semester, and I want to give you time to work on final projects. So that's it for today, and stick around if you got questions, and see you next week.